Hello everyone. I think I am audible clearly. It's a pleasure to deliver this online talk for VIT. I have given two talks before this for VIT. This is my third talk, but the first time I'm giving an online talk. I hope you guys will enjoy this talk. Given that there is this pandemic going on, I hope to take you to a different side where we discuss interesting objects about our universe, and hope at least for 1 hour, all of you would feel a little relaxed. And it's anyway always a pleasure to talk about physics. This talk is a public talk, public lecture, but I have also contained a lot of elements which are valid for physics students, mostly for BSc and master students. There may be some PhD scholars also in the audience, and I hope there are some elements which will be a little more advanced. I would request you to have to keep posting your questions, and I'll take all the questions at the end. I intend to talk for about 50 minutes, so I will stop at 7 o'clock. So today's topic of discussion is primordial black holes. Primordial black holes are extremely interesting objects in the universe. Sure? Yeah. So, yeah. But before we dive into primordial black holes, which have been told to you by the organizers that primordial black holes are black holes from the Big Bang. So we're going to discuss first black holes and Big Bang before moving on to primordial black holes. Now, black holes are, technically speaking, black holes are geometry of space and time. In Einstein's theory, space and time have geometry. They can be curved. And black hole is a particular geometry of space and time which is created by the presence of an extremely dense central object. So if you have a very, very dense central object, then the space around it is extremely curved in a way that it gives rise to black holes. Given the central object, there is always a sort of a sphere around that object. The sphere is not really made up of material, but it's a think of an imaginary sphere surrounding the central black hole. The sphere is called a horizon, and in classical physics of Einstein's relativity, nothing can come out of the horizon. So if you are an observer who is watching from outside, and if you see another observer falling into the black hole, you would never see him crossing the horizon. You will see him going slow and slow and slow, and as it approaches horizon, and the person will freeze in your frame from horizon. So horizon is a very interesting concept. For now, for our topic here, we are not going to discuss the horizon properties or geometry of a black hole. We are going to discuss about the overall presence of a black hole. So for us, the size of a black hole is roughly the size of its horizon. And the horizon size of a black hole is usually given by the mass of a black hole. So if the mass of a black hole is, let's say, mass of our sun, which is 10 to the power 33 grams, then its horizon size is only 3 kilometers. Okay. So if I say I have a stellar mass black hole or a solar mass black hole, you have to understand that the size of this black hole is roughly around few kilometers, 3 kilometers, 4 kilometers, like that. Great. So talking about geometry, I'll just show one diagram about geometry. In the top left diagram, you can see that if you have a dense object, a heavy object like sun, it sort of bends the space. Okay, this kind of bending is it's not a actual bending. It's a two-dimensional representation of what happens in the actual three-dimensional space and one-dimensional time. But it's a good illustration. If you have another compact object like neutron star, then the bending is even more sharp. And if you have a black hole, the bending is so sharp that at the center it's infinitely bent. Okay, and we call it a singularity. And around this center there is a horizon. Okay, this is all we need to discuss about geometry. Now we'll go to the astrophysics part. In the left bottom, what you can see is the so-called image of a black hole, which came up last year. This is not really the image of a black hole. It is actually imaging the material around a black hole. So the yellow color and red color objects that you see, these are actually gas and material which is moving around the black hole. And the center part, which you see as a dark circle, is actually you can think of it's roughly like the horizon of a black hole. It's a little bigger than the horizon of a black hole, but for us this is typically the size of a black hole. And this black hole has a mass of around 6 billion times mass of our sun. So it's a really heavy, gigantic black hole. There is a similar supermassive black hole at the center of our galaxy. It was discovered in the early 90s, by the fact that people carefully looked at the stars which are moving at the center of our galaxy, and they saw several stars. For example, in the right-hand side bottom figure, there are 3 stars moving in elliptical paths. And by carefully studying the curvature of this elliptic path and the period of motion, scientists have figured out that the central mass is about 1 million times mass of our sun. So it's a supermassive object. At the same time, it is located at a very small place. So it's a dense object. And in fact, the only explanation of this object is actually a supermassive black hole. So, and we believe that almost all galaxies in the universe host a supermassive black hole at the center, which is an amazing thing. So this tells us that black holes are quite abundant in the universe. These diagrams that I showed you are about supermassive black holes, but there are actually small stellar mass black holes also. We have discovered stellar mass black holes. We have discovered supermassive black holes at galaxy centers. Some of these supermassive black holes at the galaxy center would suck in objects around it and throw them as jets. So the center of these galaxies become quite active. So they are called active galactic nuclei, or AGNs. Similarly, there are giant radio galaxies, and they become giant because there are radio emission coming up because of these black holes. These are also supermassive black holes. And then recently by LIGO, by gravitational wave observatories, we have discovered binary black holes. These are 2 black holes. They are rotating around each other. Their mass is roughly around 10 solar mass to 100 solar mass. And when they rotate around each other, they give rise to gravitational waves. And in fact, they can, as they lose energy in terms of gravitational wave, they come together and collide and form one black hole. So their mass can grow by this kind of collision. So a black hole could start up as one black hole would be 10 solar mass, one would be 30 solar mass, and after a while they will merge into, let's say, about 35 solar mass, and 5 solar mass will go as gravitational waves. So we have all these ranges of masses that we see in the universe of black holes, around 5 solar mass to 1 billion solar mass. I would like to emphasize again, every time I say solar mass or stellar mass, I mean 2 into 10 to the power 33 gram, which is the mass of our sun. Okay. And such a black hole will have a size of 3 kilometers, roughly. Now, these black holes that we see, they're formed by gravitational collapse of objects, especially gravitational collapse of massive stars. So a star, a star begins its life as a molecular cloud in the universe. There's a big molecular cloud which starts to collapse under gravity, and then it collapses and its core starts burning nuclear fuel, and it stays like a star. But if it's a big enough star, then once all the nuclear fuel is over, nothing can stop gravity to compress it. So finally it gets compressed into a black hole. So this is usually how a black hole is formed. And all these black holes which are formed by collapse of stars, in this talk we are going to call them as astrophysical black holes. They are formed by astrophysical objects like a star, big star. And so their existence relies upon big stars, and big stars got formed in the universe for the first time about 1 million years after Big Bang. So when the universe was 1 million years, then only first stars were formed. So then only we could see black holes. So we should not see these astrophysical black holes before. So here is an important question, that astrophysically, why do we have to wait for 1 million years or more to see black holes in the universe? Why can't black holes form early times? Can it form earlier than 1 million years? Can it form in the early universe? The answer is yes, and that is the theme of today's topic. that black holes can form very early in the universe, much before even stars could have formed. These black holes, we are going to call them as primordial black holes. So this is our topic, primordial black holes. They are just usual black holes, but they are formed when universe was roughly 1 second old or even earlier. So when our universe today is 13.8 billion years old. So it's 13.8 followed by 9 zeros. However, these primordial black holes that we are going to talk about, they formed when universe was about 1 second old. And when universe was 1 second old, universe was mostly radiation dominated. So it was hot and dense and plasma phase. And in this hot dense plasma phase, these black holes could form. And we're going to discuss how can they be formed and what would be the implication if they are formed in the early universe. This is a vast and I would say quite active area of research. In fact, it has become recently very, very active after the discovery of gravitational waves for reasons that we will know later. There are a lot of theoretical work. I have been involved in the theoretical work. There have also been observational work. There are lots of papers coming almost every week. It involves, this is for physics students, this involves knowledge of Einstein's theory of relativity, also expanding universe, bending of light, quantum field theory, cosmic inflation, early universe, gravitational collapse, all this interesting physics. Okay, so since we call these black holes as black holes from the Big Bang, let's have a short yet comprehensive discussion about Big Bang. What do we mean by Big Bang? Big Bang cosmology, okay, the Big Bang theory. So let's see how the evolution of our view of the universe has changed over a period of last 400, 500 years. Okay. If we go back to 1,000 years back, people used to think that Earth is at the center of the whole universe. Earth was created at the center and everything else has to rotate around Earth. But following the pioneering work of Copernicus, Galileo, Kepler, Newton, we know that in our solar system, Sun is at the center and all the other planets are rotating around Sun. So we went from this geocentric view to the so-called heliocentric view. Okay. In the next image, the astronomer William Herschel tried to map out all the stars in the universe. And what he thought, that we are at the center of all the stars that we see. And our sun is at the center and all the stars are sort of around us in spherical cells. Though he didn't find a sphere, he found some kind of a pancake structure. But that was a view in 1800s. And in the beginning of 1900s, our view sort of changed. And we figured out that if in this pancake, which we call now as a galaxy, we are not at the center of this pancake, as you can see on the right side image, top right. We are actually sort of shifted from the center by about a few kiloparsec distance. So few light years, few tens of light years distance from the center, which is amazing that we are not at the center of our galaxy even. So by now people have learned that it's a big mistake to always think that we are at the center of creation somehow. So next time when Edwin Hubble discovered that universe has a lot of galaxies, people understood that we are not at the center of the universe, we are just one of the galaxies and there are so many galaxies. This bottom right figure that I show you is a 1 square degree sky, a sky as big as moon size roughly. And it has been exposed for a long time and we saw about 10,000 of galaxies in that small patch of the sky. This is taken by Hubble Space Telescope. So it looks like universe is filled with galaxies today. In fact, this is how our universe looks today. There are islands of galaxies everywhere, here and there, many galaxies, different types of galaxies. And if we zoom out even more, all these 1 square degree galaxies that you see in the left side image would become a small spot in this spider web kind of a structure. This is how the universe looks from outside. So if we could have a bird eye view of the universe, then universe would look like this complex net kind of a structure. It's so complex. There are places where you can see some filamentary structure like a web. You can also see voids in between where there is nothing. So each point here is like a cluster of galaxies. Okay, so this is how our universe looks today. So our knowledge of the universe has changed from Earth at the center to billions and billions of galaxies clumped together like a spider web, which is called the cosmic web. So this is our first take home information from this talk. The second thing is, this is how the universe looks today. But our universe has been evolving. Hubble discovered that galaxies are going away from each other. So our universe has been evolving. So the question is, did our universe look the same way all the time in past? And the investigation of this question, that whether it has been evolving or not, has been termed as this Big Bang theory, or we could say the early universe theory, or hot dense plasma theory, or even expanding universe theory. Okay. So let's discuss what is this theory. This is not a theory. Okay, let me get it clear. We always in the public, whenever we hear something like a theory, it seems like a hypothesis. No, this is a extremely well tested theory. It is as well tested as existence of atoms or existence of electrons inside an atom. And according to this theory, our universe was in a hot and dense plasma state at early times. And that hot and dense plasma state evolved slowly over 13.8 billion years to form what you see today, all these galaxies. They were not there early times. And how do we know that? To understand how do we know that, let's go to Einstein's theory of gravity. In Newton's theory of gravity, we know that mass creates gravity, and gravity is always an attractive force. In Einstein's theory, not just mass, but any form of energy, pressure, momentum, viscosity, all these things create gravity, and gravity is nothing but the curvature of space-time. To simplify this word curvature of space-time, you can roughly think that if I smear out a lot of material everywhere in the universe, I'll smear out homogeneously or uniformly, then the distance between 2 points is not going to be given by your good old Pythagoras theorem. It's not a straight line. The distance between 2 points is going to be a different curve, and it is also going to change with time. This is what we learned from Einstein's theory. And another difference is that Einstein's gravity can be both attractive and repulsive. Whenever Einstein's gravity is repulsive, we call it dark energy. This is not a topic of today's discussion, so I would not discuss the repulsive part of Einstein's gravity today. We'll mostly talk about attractive part. Okay. A black hole is a particular scenario in Einstein's theory where if you take material, rather than spreading them out uniformly, if you compress them to a very, very dense object, then it will become like a black hole. Okay. So black hole is one example. And the universe, where everything, the galaxies and material is spread almost uniformly, is a second example of gravity, where the distance between two space points, which is given by the formula which I have written at the bottom, is basically your delta x square plus delta y square plus delta z square, which is your Pythagoras theorem. But what sits in front of it is a scale factor, this a square of t. So distance is proportional to a of t. So there is some time dependent quantity which is changing with time. So let's go back to the scale factor. This is roughly like the size of the universe, and it's time dependent. So that means that if I smear out all the material in the universe, they're either going to expand or going to contract or going to oscillate. All these possibilities are there. They're most probably not going to stay static. So our universe has to expand, and this is what Hubble actually discovered in 1929. So that's a different story. We'll not go to that story. I'll just summarize what we know today. In this plot, on the left hand side, on the y-axis, I have plotted the scale factor. Think of it as size of the universe. And on the x-axis, horizontally, I have plotted time. Okay. What we see is the green curve is that initially the scale factor or the size of the universe was small. And it started increasing and decelerating, and much later it started accelerating. But it has been increasing forever since this 13.8 billion years. If you go back roughly to the very early times, in the bottom left corner of this diagram, you see that the size of the universe, or the scale factor of the universe, to be precise, goes to 0, which means that the universe was infinitely hot and dense. All the faraway galaxies that we see today were actually on top of each other. Okay. So this is how this theory of Big Bang started. So people thought probably they were on top of each other, and there was some kind of an explosion which sent them away. We don't know. We don't think about Big Bang as a scientist like that. There was no explosion. But what we know is that universe was definitely hot and dense in past. How do we know it? We know it because of the following fact, that if we, since universe is expanding today, if we go back and back and back in time, it was all the galaxies were closer and closer, so it was denser, and hence it was hotter. So if we go back enough time, in this diagram, let's say the starting point where the scale factor is 0, let's call it time t equal to 0. Starting from there until today, it is 13.8 billion years. But starting from there, if we move until about 3 lakh years or 4 lakh years, about that time, the temperature of the universe was about more than 4000 degrees Celsius. So all the atoms were in a plasma state. It's like our sun. Our sun is in a plasma state. You can't find normal neutral atoms there. Everything is plasma. Electron is no more rotating around the nucleus. Okay. So this theory predicts that if universe has been expanding and changing and evolving, then in past it must have been hot and dense and must be in a plasma state. If that was so, if it was in a plasma state, then it would trap light inside it, because plasma has ions and light interact with ions and gets trapped. A plasma is a opaque medium. So it was opaque early on, and as it was expanding, it started getting cooled and cooled and cooled. And as normal neutral atoms started forming, then this light could travel. So we should see there is a light coming far away from the past, and it's spreading over the universe. And this light should be coming from all directions. And we also know that light that comes out from a plasma phase is actually a black body radiation. So people started looking for it, and it was discovered. Well, its discovery is a very interesting story, but maybe some other time. So this left side bottom graph that you see, the solid line, black color line, which rises and falls, is actually a black body radiation from theory, and all these dots that you see are actually what they observed. So they found that there is a black body radiation coming from all directions in the sky. In fact, if you look at all the directions in the sky, this green color image that you see, this green color actually specifies, it's not the wavelength of light, it's just that it specifies the intensity of light at different directions. And since you see a uniform green color, that means almost uniform intense light or uniform temperature light was coming from all directions in the sky. This should be actually a sphere, but a sphere has been put on a plane. This diagram on the top right. This is just like map of Earth. Okay? Earth is a sphere, but we see it in the map as on a plane. Okay. However, if this is how universe started, everywhere same temperature, and it was a plasma state, and it cooled down, and the plasma became atoms, then since everywhere it was the same, the atoms would remain to be just atoms. No atom could go to any other atom because it's same in all directions. So universe will remain as a hydrogen helium gas mostly. But we see galaxies today, and we see carbon and oxygen and all sorts of chemicals, all sorts of elements. So this is not what the picture was. In fact, when people looked at it carefully, they found out that the sky is almost homogeneous, but there are small temperature differences at different places. If you see the right hand side bottom graph figure, what it shows you is the temperature all across the sky, and you see that there are fluctuations. Somewhere it's red, somewhere it's blue. By red we mean a little higher temperature, and by blue we mean a little lower temperature. And the difference between this red color and blue color is probably 0.00001 degree. So very small, tiny difference. So they are almost uniform, but very small. A small difference in temperature also mean small differences in the density. So somewhere there was a little high density, somewhere there was a little low density. This is what our early universe was. So let me show you a timeline of the universe. There is some Big Bang singularity which I'll talk about at the end. We are not sure if this really happened, but let's call it time 0. And then there was an interesting event which happened, which is cosmic inflation, which I will come to in 2 minutes. After this cosmic inflation, all the matter that you see in the universe, all the electrons, protons, neutrons were created. And then first nuclei were formed about 3 minutes, when universe was 3 minutes old. And when universe, from that time, from about 1 second or maybe even before until 60,000 years, universe was mostly made up of very fast moving particles. All the particles were moving very fast, and we call them radiation. And then from there, from 60,000 years, until about 9 billion years, universe was mostly matter dominated. It was dominated by dark matter and normal matter like atoms and molecules. Uh, the first atoms were formed about 4 lakh years after the Big Bang. First stars were formed about 1 to 100 million years after Big Bang, so quite late in the age of the universe. And today, universe is 13.8 billion years. This is the history of our universe. I will skip this slide. So if you look at this slide, on the left side, you see this big diagram which shows the evolution of the universe. In this diagram, you can see the fluctuations in temperature and density picture that I showed you before. You can see in the middle of the diagram there is this blue and red spots. Okay. Until that time, starting from the beginning until that time, universe was in a plasma state. After that time until today, universe has been expanding and universe had atoms and molecules. Slowly these atoms, because of gravity, started coming towards each other and formed stars and galaxies. Okay. So universe made a transition from a plasma phase to a cold gas phase. Initially it was in a plasma phase, then it cooled down to a cold gas phase. If there was no fluctuations present in the universe, then universe would be, today the universe would be filled with purely hydrogen and helium gas, maybe a little bit of lithium, but that's it. No stars, no galaxies, no structure. But if the universe had tiny fluctuations, as we have detected by observation, then slowly over 13.8 billion years, galaxies, stars and planets and everything would form. So once stars form, then the stars their core can collapse. At least for big stars, their cores can collapse and then they form black hole. So first you need stars to form. What we have detected is that the temperature fluctuation early times in the universe, in the plasma, was very small, as I said. If somewhere it was x degree, somewhere else it was x 0.00001 degree, very, very small. So since the initial fluctuations were very small, it took gravity a long time to increase these initial fluctuations to form structure. That's why we have to wait for millions of years for stars to form and then black holes to form. This is the real reason why. Okay, and we have detected the amplitude of these fluctuations, which is the square of density fluctuation or the square of temperature fluctuation, is about 10 to the power minus 9. So really tiny. This is the RMS fluctuation. Okay, it's really tiny. That's why it took so long. But I must mention that this small fluctuation that we have measured. Okay, first thing, any fluctuation. Fluctuation means random. So density value is varying here and there randomly. Okay, any randomly fluctuating function can be thought of as made up of a small wave, a wave with very small wavelength, then another wave with a little bigger wavelength, then another wave with a even bigger wavelength. So there are all these sorts of big wavelengths and small wavelengths. So these fluctuations that we have measured to be small is only over big angular scales, the big wavelengths. In fact, if you look at the sky and search for this light, this cosmic light which is coming from the plasma phase, then if you look from angle 90 degree all the way down to about 1 minute, 1 arc minute, then it is small. We don't know what happened when the angle is much smaller than 1 arc minute. Okay, we'll come back to it in a minute. So the origin of all the structure in the universe, all the galaxies, all the stars, this origin goes back to the plasma phase, which we have detected that this plasma phase had small fluctuations. Okay. These small fluctuations, if we leave them, if you look at this right hand side diagram, where you have 4 boxes, blue colored boxes. So if you leave these small fluctuations, initially to start with, look at the left side top diagram, blue box. It is very early universe and it is filled with, let's say it's filled with hydrogen and helium gas. Actually, it is not. This diagram is for dark matter, but I am just simplifying it. It is made up of hydrogen, helium gas and dark matter, let's say, and it has very small fluctuations, so it looks very uniform. We let time pass and then we let gravity do its act. So you see slowly as you go from that figure to the right hand side, then to the diagonally opposite. So go from your top left to top right to bottom left to bottom right. This is how the structure grew and finally it formed in the bottom right. It formed this spider web kind of structure helped by dark matter. dark matter have a property, they provide extra gravity for structure to grow, so structure grows a little faster in presence of dark matter. Okay, and this process takes millions of years. That's why stars are formed after a million years at least. These are the origin of this astrophysical black holes, the black holes that are formed due to collapse of stars. Okay, now since we said that we have seen these fluctuations only over large angular scales and they are small, what if these fluctuations are not small over small angular scales in the sky? Like we go to angular scale which is less than 1 arc minute, and from there we go back up to angle which is 10 to the power minus 20 arc minute. Very, very small angle. We can't resolve it very easily with our telescopes now, but there are all these scales which are there. If on those scales there are large fluctuations, large temperature fluctuations in the early universe, then interesting things can happen. Very, very interesting things, in fact. All these fluctuations that I'm talking about, which were there in the plasma, was actually produced by an event called cosmic inflation, which was much before this plasma phase. Let's call this plasma phase as the hot Big Bang phase. Okay. And this cosmic inflation came before this hot Big Bang phase. And this inflation can be explained very easily by a diagram of a hill or a potential. You see that there is a hill which is from right side, if you approach, it is coming down, and then there is a minimum. And it's as if a ball is rolling, this red color ball, it's rolling down this hill. Initially the ball rolls slower, and later it goes to the minimum and starts oscillating. The principle of thumb is the following, that as long as the ball rolls slow and slow, the amount of fluctuations in the plasma it produces is very, very small. In fact, if you look at this blue color star in my diagram, in the top diagram, and also go to the bottom diagram and see the blue color star, when the ball was near this point, it created fluctuations of the amplitude 10 to the power minus 10, which we are talking about. The RMS value is 10 to the power minus 10, which means temperature fluctuation would be around 10 to the power minus 5. And as the ball rolls down this smooth hill, the fluctuation amplitude actually decreases on small scales. So in the left hand side bottom diagram, if you go from right hand side to left hand side, the angular scales are decreasing. Okay. So in the blue star, these are like about 1 degree angular scale. And if you go down and down towards the left of the diagram, you see that the green color and the red dot, the dotted red color diagram is actually going down and down. So this means that there is less and less RMS fluctuation. So the maximum fluctuation you had was about 10 to the power minus 5. That's why it would take at least 1 million years for black holes to form. But the scenario could be different. The scenario could be that even though, now focus on the right hand side top diagram. So now look at this blue color star and the red color ball. When the ball was near this blue color star, then the fluctuation was small. This has been observed. But as the ball rolls down this hill, if the hill has a flat plateau-like place, which I call the PBH feature, the primordial black hole feature. If the ball reaches near this flat plateau, it slows down. And the rule of the thumb is the slower the ball rolls down, the higher is the fluctuation. Okay. So initially the fluctuations were smaller when it was at the right hand side corner where the red ball is, and as the ball rolls towards the left hand side, it slows down in its velocity, so it creates more and more fluctuations. And this thumb rule is coming from quantum mechanics. Quantum mechanics actually tells us that if the ball is rolling faster, it has smaller fluctuation, and if it is rolling slower, it has larger fluctuation. So let's see the amplitude of fluctuation right now because of this PBH feature or this flat kind of region in the potential. If you look at the bottom right figure, you see that the green color curve starting from the blue color star, if we go towards the left, it was going down, 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 and somewhere there is a sharp peak in the fluctuations. So there is a bump, there is a sharp bump, and this sharp bump means it creates large fluctuations in temperature and hence large fluctuation in density. In fact, this fluctuation is so large that in the early universe, if we have this kind of fluctuation in the plasma state, it is going to compress the plasma very much. Fluctuation means somewhere density is higher, somewhere density is lower. So if fluctuation is high, there is a very high density place in the early universe, even though it's a plasma state. And this high density place actually gets collapsed by gravity because it's so dense. And then they form black holes. and these are the primordial black holes. So by this mechanism, I know this mechanism is a bit difficult to understand, but I thought there are some physics students in the audience, so I tried to explain it a bit. So the bottom line is that there are fluctuations in the early universe. The fluctuation on large scales are small, but the fluctuation on small scales can be large. We have not detected it yet, but they can be large. And if they are large, they would form primordial black holes. Okay. This is a little complicated diagram, mostly meant for physics students. What you see is a green color curve going down and then going up again as you go from left to right, and you see this blue color line. Okay. So what this curve represents is that during cosmic inflation, a lot of fluctuations were created by quantum mechanics. When they were created, these fluctuations go outside the observable universe. So they have this property. During cosmic inflation, the universe actually expands exponentially. So it stretches out all these fluctuations to very, very large distances. In fact, greater than the observable universe. So they go outside, they carry their fluctuations and go outside. And much later, when inflation is over, the universe catches up with these fluctuations. So they come inside slowly one by one. What we have seen is that on large scales, whatever fluctuations have come in, large wavelength fluctuations, they have very tiny fluctuations and they form the structure in our universe. But on small scales, we yet have to observe. We have not observed it. And they could be large fluctuations and they could form primordial black holes. Okay, so I will skip it for now. I'll go back to more standard stuff. So these primordial black holes, which I explained how they are formed, even if you didn't understand thoroughly how they are formed, it's a complicated topic. Let's discuss their implications, which is much easier to understand. The first implication of primordial black holes is that their mass could be very small. This is an interesting thing because the astrophysical black holes that we discussed before, the black holes that are formed because of the collapse of stars, okay, they would have a minimum mass of one stellar mass. So their mass would be at least one times mass of sun, at least. But these primordial black holes, since they are not formed because of collapse of stars, they could have a mass which is as small as possible. In fact, from observational bound, we know that their mass could be actually as small as 10 to the power 15 gram. Let me tell you that 10 to the power 15 gram is the mass of Himalaya. So their mass could be a Himalaya mass, which might seem to you a big mass compared to a mass of a human being, but compared to the mass of a star, it is nothing because mass of our sun is 10 to the power 33 grams. So it's much, it's billions and billions of times smaller than mass of sun. Okay, and the size of this black hole, which is 10 to the power 15 gram, would be like size of atomic nucleus. They are very tiny. You can actually inhale them. They are so small if they are there nearby. And these black holes could also be big. They could be as big as 10,000 times mass of sun. They could be as massive as 10,000 of sun, and their size will be these big ones. Their size will be about 30,000 kilometers. Okay. So interesting things that they could have all these ranges of masses. Second thing is they could form dark matter in the universe. So we know universe has dark matter. We usually think of them as this dark matter is they're made up of some new particles that we don't know, but they could be actually primordial black holes. If they are primordial black holes, we don't need any new particle. Whatever radiation was present in the early universe in the plasma phase, they got compressed because of high fluctuations and formed primordial black holes, and these black holes have been behaving like dark matter ever since. They could also explain the origin of the binary black holes that you see in the LIGO events, okay, the gravitational wave detectors. What they see is that there are two black holes rotating around each other and then they merge. Okay, the question is, how do two black holes came together? Okay, it's a very open and hot topic in physics right now. If you naively think that there were two stars, they were rotating, and the first star collapsed to form a black hole, the second star also collapsed to form a black hole. That's how the binary is formed. This is unlikely because when stars collapse, the outer part of the star goes in a burst, which is called supernova. So if they were nearby and rotating, the supernova will actually blow the two black holes away. So there are complicated astrophysical techniques how they could be formed, or they could be primordial black holes. They were formed early times in the universe. There was no supernova in the process in which they were formed. So some random two black holes found each other by gravity, and they have been rotating around each other ever since. This is a very important topic, but I don't have enough time to talk about it in this talk. They can also explain the presence of these billion solar mass black holes at the center of galaxies, especially at the center of active galactic nuclei. As I first talked, there are these billion solar mass black holes present at the center of galaxies, and they have been present when the age of the universe was about less than 1 billion years. So the question is, how are they formed? If black holes are only formed by a collapse of stars, then how did so early in the universe so many stars collapsed and came together and formed these black holes? This is an open problem, and actually primordial black holes can explain it, because first thing is their mass could be very big when they are formed. Second thing is they have formed so early that they have enough time to come together and grow in mass. Okay. Third thing is they could probe the small scale primordial physics or early universe physics, which we don't see because they are smaller than 1 arc minute. So we don't see them usually in our telescope, but if primordial black holes exist, they will tell us that, okay, at small scales there was large fluctuations. This is a very important topic. Again, I will not go into it. Then the sixth one is, could this this primordial one of these primordial black holes be the ninth planet that we are looking for? I will talk about it in a minute. Okay, I have a lot to say about, not a lot, but a bit to say about this ninth planet. I'll come. But another very interesting and fundamental thing about primordial black holes is they may help us to test the famous Hawking radiation. What I told you in the beginning is that black holes are a structure of space-time, and there is a horizon, and anything which falls inside the horizon doesn't come out for the observer who is outside. But Hawking said this is only classical physics. If you apply quantum physics, then actually whatever falls into the black hole comes out as a thermal blackbody radiation. And so the black hole's horizon looks like a hot sphere, and this sphere has a temperature. But even though I said it's a hot sphere, its temperature is actually very, very low. In fact, at the bottom I have written a formula. Let me interpret the formula for you. That the temperature of this temperature is called Hawking temperature, the hotness of a black hole, which is due to quantum mechanics. And the temperature of a black hole will be around 10 to the power minus 8 Kelvin if the mass of the black hole is same as mass of our sun. And in fact, the temperature, so if our sun becomes a black hole, in bracket, our sun will never become a black hole, but suppose our sun would become a black hole, suppose. It will have a temperature of 10 to the power minus 8 Kelvin, which is very low, and you cannot test it using thermometers. Okay. And if you go to bigger black holes, they have even smaller Hawking temperature. So to really test Hawking radiation, you need smaller black holes. But astrophysical black holes are bigger. They're formed from stars. They cannot be small. However, primordial black holes could be very, very small. Since they could be very, very small, so their Hawking temperature could be as high as 1 Kelvin or 100. So if they are there, they will radiate like a bomb, like a burst, and we should be able to see them. And this is how we look for primordial black holes in the early universe. This is one of the ways that we look for them. Okay. So we can test Hawking radiation. Okay, so let's see the relation between the mass and radius of a black hole. This radius is the size of this horizon that I am talking about. And what we see is that if a black hole's mass is same as mass of our sun, then it will have a 3 kilometer size. Okay, so if a black hole is as big as massive as our sun, it is 3 kilometers big. So it's smaller than, I'm in Pune, so it's much smaller than Pune. It's a small one. Okay. And next, I have given a list of black holes and their masses and size. The image of the black hole, the supermassive black hole in M87, which you saw in news last year, it is about 6 billion solar mass. So it's 6 billion times mass of sun, and its radius is about 10 to the power 10 kilometers. So 10 billion kilometers, quite big, almost as big as our solar system. Then sun mass black hole is 3 kilometers. Then Earth mass black hole. If a black hole has a mass of Earth mass, then it will be about it will be about 10 millimeter. It's quite tiny, a small one. And if you have a lunar mass black hole, moon mass black hole, it is even smaller than 1 millimeter, tiny black hole. An asteroid mass black hole would be about few micrometer, like a cell, like human cell. And Himalaya mass black hole, which I told you, is about size of a nucleus. So these are primordial black holes which could be really, really small, tiny. And they could be forming dark matter in the universe. So they would be moving around here and there. Okay, so primordial black holes can also explain something called search for ninth planet. So what we have seen at the outer part of our solar system, there are many trans-Neptune objects. Trans-Neptune in the sense, these objects, they are rotating away from Neptune. So they are further than Neptune. And many such objects have seen to have aligned their perihelion, their closest approach to Sun. And this could be explained easily in Newtonian gravity if we introduce a new object that we have not seen. And its mass should be about 5 to 10 times mass of our Earth. So there is some new object whose mass is about 5 to 10 Earth mass. This can explain a lot of observation. So in fact, somebody wrote a paper last year showing that if it is a black hole, this object, if it is a primordial black hole, its size will be as big as this black dot that I'm showing you. It's smaller than a baseball, okay, a very tiny black hole, but it has a heavy mass, almost 10 times mass of Earth, and it can explain all this observation. If you want to hear about the ninth planet and the search, there was a wonderful talk given by Professor Surhud More from IUCAA. I think last year. It's available on YouTube, so you should watch it. It's called Hunting for Planet 9. So I have now talked about the things that I wanted to talk mostly. The last thing that I want to talk is the observational signature of these primordial black holes. In this plot that I'm showing, what I have in the x-axis is the mass of primordial black holes, and what I have in the y-axis is what fraction of dark matter these primordial black holes are making. So if y-axis is 1, it means all the dark matter is made up of primordial black holes. If y-axis is 10 to the power minus 1, which is 0.1, it means about 10% of dark matter is made up of primordial black holes, and so on. And all these shaded places that you see, the gray places and the red places, are the places which are ruled out by observation. So at those places, primordial black hole could not be there. But there are a lot of white places where primordial black holes could be present. And this is what we are searching for. Especially observational astronomers are looking for them by different kind of means. I wanted to talk about primordial black holes and their signature through gravitational waves, but I think I'll skip it given that time is almost over. Just want to mention that the mass of these primordial black holes depends on when these first thing, the primordial black holes are formed in the early universe because of the presence of very, very high fluctuations at small scales. And these fluctuations go outside the observable universe during inflation, and they enter the observable universe much later. The mass of these black holes depend on when they enter the universe, these fluctuation wavelengths. If they enter early times, then these black holes will be tiny, like Himalaya mass. And if they enter later, then they could be 1,000 times mass of Sun. So this is another diagram, but I'll skip it. I'll not describe the details. I will mention a simple thing about gravitational waves. I'm skipping a bit, just a minute. Yes. So what happens is that in the early universe, during this inflation, which produces these quantum fluctuations in density, the inflation also produces quantum fluctuations in the space-time itself. So it makes space oscillate. And so it produces gravitational waves. Usually the gravitational waves are produced are very, very small because the density fluctuations are small. It's 10 to the power minus 4 as we have seen. But on small scales, as I told you, density fluctuations could be much higher. Since the density fluctuations could be much higher at small scale, they actually can induce more and more gravitational wave in the early universe. So they can increase the amount of gravitational waves in the early universe. For physics students, this is going to be a research field for next 10 years. And so you may like to read about it. I've given some references here. So there could be gravitational waves because of these primordial black holes, just because of their existence or their formation, because they are formed from high fluctuations. Okay, so now concluding remarks. that there are primordial black holes are extremely interesting objects, which have important cosmological and astrophysical implications. Like they could be dark matter, we could test Hawking radiation by them. They could explain the ninth planet. They could explain AGNs. They could explain binary black holes that LIGO see. There has been a lot of theoretical progress and very recently some observational progress. Then for future, there has been two important implications of these primordial black holes for gravitational waves observation. For example, they could be the binary black holes that LIGO is detecting. This is first case. The second case is, as I told you, in the early universe, since they are formed by heavy fluctuations, heavy fluctuations also happen in the space-time, and so a lot of gravitational waves are created in the early universe also. So by detecting these things, we can know about them. You could contact me if you want more. I want to send, I know this is a difficult topic. I want to give a take-home message before I stop. Even if you have not understood most of it, take these messages home with you. These are the key concepts. That our universe was a hot, dense plasma early times. Then it cooled down to form the present-day universe, which is the island of galaxies and looks like a cosmic web. Okay. If temperature and density fluctuations were absent in the early universe, then today our universe would be smooth hydrogen and helium gas without any stars or galaxies or black holes. But our universe had tiny fluctuations of temperature and density. And these tiny fluctuations which were present, they were tiny over large angular scales, like from 90 degree to 1 arc second. So the big wavelength waves were actually had small amplitudes. Okay, they form the structure of the universe. So all the galaxies and clusters, this cosmic web that you see, they are formed due to these tiny, small, large scale fluctuations. But there could be large fluctuations on small scales. So fluctuations are small on large scales. Fluctuation could be large on small scales. If these large fluctuations are present, they can form primordial black holes, and they are formed when universe was less than 1 second old. So they are really old objects. Okay, while the astrophysical black holes are formed when universe is at least 1 million years old. And this mass of these primordial black holes could be as small as mountain mass, and their size could be as small as a nucleus size. Okay. So since black holes are extremely interesting objects and so many physicists, so many scientists and philosophers have thought about them and have been in awe of these black holes, primordial black holes would be even more interesting because they have been formed in the early universe without ever having a star. Subramaniam Chandrasekhar, who is an Indian physicist and Nobel laureate, who said that black holes are extremely perfect, big microscopic objects. They're beautiful objects. This statement may not be correct. For example, following Stephen Hawking, we know that black holes could be even microscopic because from this talk, black holes could be nucleus size also, even smaller also. So they could be microscopic and highly quantum mechanical. Then they could be radiating a lot of photons out of them. So this is our viewpoint that has changed over time. I worked on a project and wrote a paper on primordial black holes. This might be technical, but for physics students, you are welcome to read. And this work was featured by a couple of places on Astrobytes in December, and this was also this also came in Indian Express. I think in early April, which I have posted here. Anyway, thank you very much.
We definitely have a lot of questions. I have chosen a few and I'll pass it on to you. The first question that I have for you from Dilip Sonkar. He's asking, what do you mean by one-dimensional time when you said one-dimensional space and one-dimensional time?
So I said three-dimensional space and one-dimensional time. In the sense that we see in the universe that space is three-dimensional. I can go back and forth, forward, backward, or up and down. So there are three space dimensions, and there is a time which is flowing in the universe. So there is only one time, as far as we know. If time is more than one dimension, that could be lot of paradoxes. So that's what I meant. But why did I call time as as a dimension? The reason is in Einstein's theory of relativity, uh, when objects move from one point to another point, the time and the space that we note change depending on the observer. In Newton's theory, if an object goes from at 8 o'clock, it goes from this point to at 9 o'clock to this point, then every observer will say it started at 8 o'clock and ended at 9 o'clock. But in Einstein's theory, we know if another observer, which is moving with respect to the first observer, if he also says this is 8 o'clock, he may not say it ended at 9 o'clock. The time could be longer. Okay. So that's why we have to look at space and time both together as dimensions.
Yes, that was pretty insightful. The next question is quite of theoretical. Next question is from Weber Brawat. He is asking how are mass limits of PBH derived? How are those mass limits derived?
Oh, first thing is Vaibhav is my friend, I guess. So, how is the mass limits? There are no limits actually. In fact, primordial black holes could be as theoretically they could be as small as something called Planck mass. Planck, we would not talk anything smaller than Planck mass because we don't understand physics smaller than Planck scale. But they could be as small as 10 to the power minus 7 gram, minus 5 gram. But these black holes, which are so small in mass, we saw that Hawking temperature, which we maybe I should go back to that to show it. It would be nice. Just a minute. Yeah, so what we saw is that Hawking temperature is inversely proportional to the mass of black holes. And a solar mass black hole would have 10 to the power minus 8 degrees Celsius, while 10 to the power minus 5 gram black hole would have so much of high temperature, 10 to the power 20 or something, that it will burst out gamma rays, very high energetic, and it will evaporate out completely. So in fact, any black hole whose mass is smaller than a Himalaya mass, 10 to the power 15 gram, would have evaporated by now. So they would start off as black holes and behave like dark matter, and slowly over time they will radiate out, and they will become like radiation. But we don't see that. So there is a constant that there are not many primordial black holes whose mass is smaller than 10 to the power 15 gram. So this is how the one limit comes. The other limit, the higher limit, which is 10,000 solar mass. If primordial black holes are higher than 10,000 solar mass, in the early universe they are formed, they will start accreting light, especially this cosmic light or CMB, cosmic microwave background light. As they accrete this light, the light will get distorted. And we have actually detected this light, and we know the amount of distortion which is there. So from there we know that these black holes could not be very massive. So that's how there are two limits.
I hope he's satisfied with the answer. The next question is from Raj S. Even I have the same question. How was the cosmic web image formed? Like in what frequency? Like how was the image captured? We are inside the universe, and that means we are inside the web. So how did we take that picture?
Oh, it's a fantastic question. First thing is the picture that I showed is not a real picture. It's a simulation. It's a computer simulation. In the simulation, we started with smearing out a bunch of dark matter particles early times in the universe, and let this bunch of dark matter particles evolve for 13 billion years. So initially they were almost uniform, but wherever there was a little higher density, it started to collapse under gravity, and then it formed this wave-like structure. We don't see the wave-like structure like this if we want to see in the sky directly in our eyes, but we can find out the position of a lot of galaxies in the sky. So we'll focus in some angle. Let's say we focus in this angle, and we figured out where all the galaxies are and figured out how they're positioned. Okay. Then we can plot it from our viewpoint, how they look. And now let me show you a real diagram, how it looks. I hope I have a diagram, a real diagram. I think I have, yes. Is this diagram visible? Okay, this is now a real diagram. This is the real diagram that has been taken. We are at the center, and we have looked in two different directions. Each dot here is a galaxy. The color coding, forget about the color coding for now. So each dot is a galaxy. This is the position of a galaxy. We have carefully placed them. This is going back to many billions of light years in distance. And so you see this wave-like structure. So just like staying on Earth, we can figure out that Sun is at the center, Earth is not at the center, and all the planets are rotating around Sun. And we can think of a bird's eye view of our solar system. Similarly, these figures are done.
Thank you so much. This is the first time we saw this image. Thank you.
Uh-huh. Yeah.
So for the next question is from MK Slab. He's asking, how do singularity of zero dimension turn into three-dimensional universe?
This is again a fantastic question. Okay, I didn't talk much about Big Bang singularity. Even though classical physics, if you extend classical physics, you see that there should be a singularity. But we know that every time we have a singularity, quantum physics removes it. In fact, we have had singularities in just electricity, in the theory of electricity. And quantum physics always removes singularities. So we believe that there are no actual singularities in the universe. Just that every time you find a singularity, you know that your laws of physics are not applicable there. So in the very early times in the universe was so dense and so hot that all the laws that we have discovered till now do not apply there. So we are now trying to study this early universe very carefully and try to guess what was the law. In particular, we have to form a quantum physics version of Einstein's theory, which we don't have proper. We don't have a complete theory of it. So once we have it, the singularity would be removed. And what it would become, we don't know. There are lots of possibilities. It's possible that universe was big and three-dimensional, and it was contracting initially, and at some finite size, it started bouncing back. That's possible. It's also possible that universe was static of some size for a while, and then it started expanding. It's also possible that there was nothing in the beginning, and universe tunneled out quantum mechanically out of nothing. All these ideas are interesting ideas are there, which maybe we would know in next 30-40 years. Okay.
That was great. He further asks he could not understand fluctuations going outside the universe. What are those fluctuations?
So actually, what I meant is fluctuations going outside the observable universe, not the whole universe. So by fluctuation, let's say you are looking at a pond, okay, or a swimming pool, and the rain is happening. So there are lots of random waves fluctuating. So the surface of the swimming pool is fluctuating actually. And this random fluctuation can be thought of as a very small wavelength waves plus a little larger wavelength waves plus even bigger wavelength waves. So there are all sorts of wavelengths. This is called, for people who study physics, this is called Fourier series. Okay. So writing any random function in terms of sine and cosine functions. So you have all sorts of nice wavelengths. They add up to form all these random functions. During cosmic inflation, the universe was expanding so fast that all these wavelengths are stretched very fast. So fast that they go outside our observable universe. But then cosmic inflation ends after some time, and then expansion is no more that fast. So after some time, these waves which were outside our universe, now our universe catches up with them, and so they slowly enter. So when they enter, whatever was the fluctuation, we could see it on large scale. That means over a large scale, we would see a variation of density, varying from high density to like a crest and a trough. Okay. Similarly, there will be another wave coming. This is what happens. It's a little complicated concept, but
Yes, that was insightful. There's one important question I find from Priyambada. She's asking, can gravitational waves as detected by LIGO be distinguished As coming from a PBH merge or a ABH merge or a combination?
Can we distinguish? Oh, this is a wonderful question. I think Priyambada is my friend Priyambada. It can be distinguished. It's a complicated process. One of the ways to distinguish is that the spin of the black holes are different. There is a particular parameter. I think I have a slide on it. So there is a particular parameter which is related to the effective spin of the two black holes as the two black holes rotate around each other. Uh, the effective spin for usual astrophysical black holes are usually, again, this is not absolute statements, they're usually supposed to be higher. And what we have detected from LIGO events, whatever events we have till now, the confirmed 10, 12 events and the candidates which are 30, 40, the spin parameter is quite low. In fact, this diagram shows the effective spin, chi effective, for different events, and you see that the middle line, which is 0, everything is very close to 0. This is expected from primordial black holes. If black holes are made up of primordial black holes, not formed because of collapse of stars, then these binaries would have a chi effective which is very close to 0. So this is one way of distinguishing. And now there are other ways that I have some rough ideas. I don't think this thing has been tried before. For example, if primordial black holes are making dark matter, their position should be very highly correlated to dark matter. While normal black holes, astrophysical black holes, which are made up of normal matter, they should be following wherever normal matter were in the universe. Even though the dark matter and the normal matter are very close to each other in the universe, there is a slight shift. It's called bias. So this bias should be seen in astrophysical binary distributions as compared to primordial black hole distributions. So there are these two ways that I know of that you can check. Plus primordial black holes, their existence also brings us early universe gravitational waves, which I talked about. Just by their presence, they will bring up a lot of early universe gravitational waves. So
We are already taking much time, so how much more questions
so
can we take? Like, how are you comfortable?
maybe two more questions.
Okay,
Yeah.
fine. So there's one question from Ratan Deshpande. He's asking, when you said stellar black holes can have masses equal to one solar mass, but as per Chandrasekhar limit, the core has to be more than 1.4 times the solar mass to undergo a supernova.
Yeah.
Like those, there's some the relation.
Yes. Yeah. It's a very valid question. So what I meant by one solar mass is the order of one solar mass. So to be safe, we should say 5 solar mass or something like that. 3 solar mass. There is a gap. There is a mass gap between what should be the mass so that you are a black hole or you are a neutron star. So there is a mass gap between around 2.5 solar mass to about 4 to 5 solar mass. So okay, so to be safe, you should say 5 solar mass or 10 solar mass. 5 solar mass is fine. But remember that we are not talking about in the order of solar mass. We are talking about 10 to the power minus 20 solar mass to 10 to the power 4 to 5 solar mass. So in this order, 1 solar mass is equivalent to 5 solar mass. So take it as an order of magnitude.
Okay, I got the relation to some extent. There's one last question from our Antariksh member Nishant Pawar. He's asking how the cosmic microwave background radiation sustained for nearly around 13 billion years, that is the age of the universe, would it get reduced as the time progresses?
Very good question. So the question is what gets reduced? What gets reduced is their frequency. So the energy of each individual cosmic microwave background photons get reduced as the universe expands over time. So when they were emitted, universe temperature was about 4000 degrees Celsius. So they were probably yellow light, yellow color light. But now, as the universe has expanded for 13 billion years, their wavelength has gone from yellow light to microwave light. So yes, so what has reduced is their frequency. Their wavelength has been getting stretched, so frequency is reducing, so energy is reducing. But their number is almost the same. because most of these photons don't interact with anything. So they directly come from this time, hot Big Bang phase, to us. So their number is almost a constant. There are a few observations here and there, but mostly they're constant.
Any last piece of advice that you would like to give?
Oh, I know it's a difficult time for everyone, whatever is happening in the world. I hope thinking about the universe and thinking about that our Earth is a small place in the whole big universe actually gives us a philosophical and psychological way to feel happy that it's okay that something bad is happening in the universe, and maybe we can overcome this period and again be come back to the normal life. So
That was very insightful. So I'll just switch on the transition. I'll just conclude. Yeah. So I think this lecture have was very insightful. I would really like to thank Mr. Swagat Mishra for giving this talk. And th- th- this year we have completed for Antariksh, we have completed 10 years, and this part, a lecture series, was just a beginning. We would take lectures on astronomy, astrophysics, and even the technical aspects which are used. Uh, it was great having you, sir. Now I would like to make a small announcement. There's one, yeah, just a second. Yeah. So there's one thing coming up. Ayuka is planning a Swantina 20. That is a Swan antenna challenge, wherein you can form up teams. It can be of research institutes, educational institute, college. You need to have one mentor and your team. You need to make an antenna which would work at low frequencies, and that should be of just a second. Yeah. Uh, Ayuka is inviting team from various educational and research institute to participate. It is an opportunity to innovate and become one of the architects of the Indian Skywatch Array network. The challenge is to design and develop a novel broadband dual polarization antenna element, and it is suitable for astronomical observations at very low radio frequencies. Uh, so this is a good opportunity for everyone to really get into what's happening around in astronomy around the world, and I would think all of us will surely take part in this. I have added this link to the description box. Please go through it. Well, I'd like this. It was a great session, and thank you everyone for watching. Thank you.